In this final session, we're going to cover running Pilot in parallel, both on a desktop and on a cluster. And the topics we're going to cover will be, in addition to running in parallel, as part of that will be optimizing Pilot performance. How can we best select the components and output options for getting the best performance out of Pilot? We'll touch on when you need to build Pilot from source, how to use Pilot with a queue system. Pilot has built-in interfaces to several popular queuing systems that are used in clusters that makes it extremely simple to submit a Pilot job to a queue system. And we'll also discuss Pilot performance. So two things to point out are in terms of running in parallel. On a laptop or desktop, you generally run Pilot for problems related to what we call strong scaling, in terms of we use more processes or cores to reduce the runtime for a given problem. And so our problem size doesn't change, we just use more of the computational resources available on the machine to reduce the runtime. On a cluster, we may be using this strong scaling of distributing the floating point operations among processors, but also, in many cases, we want to run larger and larger problems, and so we'll have about the same workload on each processor, and then we just use more and more processors and cores as our problem size increases, and that's called weak scaling. Some things to note is on a cluster, you must build Pilot from source as well as its dependencies. This is to ensure proper configuration for the cluster hardware, and in particular, how the different compute nodes communicate with each other using the message passing interface. Running on a cluster requires some additional parameters related to the batch submission, and we'll go over those. And in terms of how to run Pilot in parallel on your laptop using the binary, all you have to do is add the command line argument to your normal command line arguments of -- nodes equals, and then the numerical value for how many cores. Such as if you want to run on 2 cores, use the number 2, run on 4 cores, number 4. It'll spawn that many processes, they'll show up on different cores. You don't want to use more processes than you have number of cores, because then they just start fighting each other, and your machine will slow to a slow crawl. How does Pilot run in parallel? Pilot uses what we call the single program multiple data parallel processing model, where each processor or process runs the same code, so it's running a single program, but there's multiple data. And so that refers to the fact that we're dividing the volume up into pieces so that each process works on its own part of the volume. And so they all solve the same numerical equations, but they're operating on a different portion of the domain, and then the inter-processor communication is to keep everything in sync across each time step. In Pilot, we start out in running in parallel with process 0 reading in the mesh. It adds the cohesive cells by adjusting the mesh topology. It then partitions the mesh and determines which vertices are shared by multiple processes. So each file in that cell appears only on one process, but then at processor boundaries or process boundaries, there are vertices shared. And so we have one process will own a vertex, and then on the other process, it'll show up as what we call a ghost vertex, in that it knows which process to get the values from and how to communicate with that process. Finally, in step 4, we distribute the relevant portion of the mesh to each process, and then we can begin doing the final initialization steps of all processes working in parallel on their own part of the mesh, and then we begin solving the equations. Right when we load up on each of the processes in parallel. There is an option of doing a global refinement to reduce the cell size by a factor of 2, or you can think about it as increasing the resolution of our simulation by a factor of 2. And this allows us to solve a larger problem than what we could if we had to read in our fine mesh over just on process 0. So our main sort of bottleneck in terms of the total size of problem that we can run is being able to read in the mesh on a single process. In many cases, generating the mesh is, for example, using qubit, you may run out of memory in generating the mesh before you would run into this bottleneck of being able to read the mesh in. And so being able to read in the mesh, attach the cohesive, generate the cohesive cells, and distribute the mesh all on a single process. And right now, in terms of running Pilot, that is the main bottleneck. In the future, we hope to remove this bottleneck by starting up and having each process would read in a portion of the mesh. They'll do some sort of cleanup to make sure the mesh is partitioned in the best balanced way, and then they can start running. This is an issue pretty much with all parallel codes, the fine element parallel codes, especially those with unstructured meshes. In unstructured mesh, you really have to have an idea of the entire mesh in order to partition it in a load balanced way so that you don't run into one process doing a lot more operations or using more cells than the other ones. So let's focus now on looking at how to optimize Pilot performance so we get the most out of the code when we do run in parallel. One of the key areas is output. When we're running in parallel and using multiple processes, we don't want Pilot to spend much time doing output, and so we want the output to be as efficient as possible. That means we don't want to use VTK output. VTK output is inefficient for several reasons. One is that the VTK output in version 1.9 is purely ASCII. Writing ASCII files is much, much slower than writing binary files. And in this implementation of the VTK output, which is generally true for what's called the legacy output for VTK, each process sends its data to process 0 for writing. So we have to end up with just a single file. And so what we do is we send all information to process 0 for writing. In sort of more recent versions of the VTK file format, you can write things out in sort of some binary blocks within XML files. It's still not very efficient, but you can start to write in parallel. A much better approach is using binary files like HDF5 because each process then can write its own data in binary, in parallel, taking advantage of things like parallel file systems and file servers with large RAIDs. And so whenever you're running a large research problem, we strongly recommend that you use the HDF5 output. It also makes the post-processing of the data much easier because you can use high-level interfaces such as like MATLAB and Python that we went over in the Greens function inversion case, where it takes 3 lines of code to get the information out of the HDF5 file. Solver performance, as we'll see that for the quasi-static, it's very important to choose the proper solver parameters because so much of the time in large research problem is spent in the solver step for the quasi-static. Right now, we recommend so the field split algebraic multigrid is scaling in almost all cases better than additive Schwartz. You can also play around with the solver 07.cfg settings that Matt discussed in the solver tutorials. And that solver7.cfg file, you can get a link to it from the agenda page. There'll be a link to the solver parameter files there that's posted on the website. For dynamic cases, the solver really isn't an issue because we have, with explicit time stepping, we have a diagonal matrix on the left-hand side, so everything is decoupled. So a trivial solve scales extremely well because all the operations are local to the processor. It's the computing the residual that involves some communication as well as doing some updates in the initialization part that involves some communication. So there is interprocess communication in computing the residual and doing updates, but actually advancing the time step once we've computed the right-hand side does not involve any communication. Overall performance, some things to keep in mind is that the speed of your memory and the connection between memory and the actual core, processing core, is more important in most cases than the actual speed of your CPU. So that means when you look at things like specs of computers, having a 3 gigahertz CPU is not as important as the memory bus speed that tells you how fast you can transfer the values from memory to the CPU. Now, if you have different other classes of problems, that's sort of non-finite element type problems, non-finite difference type problems, where you really have, say, a dense matrix, a small dense matrix that's sitting in memory, and you're operating on things that are mostly right there in your memory cache, then it is just sort of raw CPU speed. But with our large sort of memory usage and finite difference, finite element type calculations, it really is limited by the speed of the memory bus. And we'll see that when we look at some log files, and we'll see sort of our performance starting to saturate when we hit and saturate the memory bus. You may get some marginal speed improvement if you compile the source for your hardware, such as for your particular version of hardware of, say, your desktop machine, because we've generated our binaries basically just using the GNU compiler with sort of good but not super high optimization. You can use higher level of optimization, remove some of the debugging checks that are in there to help speed it up just a little bit more. So let's look at running Pilot on a desktop. As I mentioned before, all you have to do is add in a single command line argument, --nodes equals, and then the number of cores. The Pilot binary, the restrictions on the MPI that we've included in the binary is that it allows inter-process communication only within a single computer. So that's referring to the fact that on a cluster, you have actually separate CPU boxes connected over a high-speed network. And so our MPI that we have in the binary only allows you to communicate between cores on a single, within a single sort of motherboard, or between processors on a single motherboard. And so it works on laptops, it works on desktops, and you can run it on a single compute node in the cluster because that essentially acts the same as a laptop or desktop. So you access on a cluster, and so from building from source, as I mentioned, you can get some modest performance gains to optimize it for your hardware if you choose to do so. Okay, so let's, any questions so far about running in parallel? Okay, so let's run some of our examples that we've been looking at in parallel right here on my laptop. So here's our good friend 3D Hex 8, and let's run step, let's start out with step 03 in parallel. So I'm going to run on 2 cores. I type step 03.cfg -- nodes. And so in terms of what was happening, You can see all our same initialization, and so and the solver looks the same. And one thing you'll notice that here in the putz log summary, it does show that I did indeed run on 2 processes. If I scroll down and look at the summary here, notice that I do have there were 205 MPI messages. This says the lengths of those messages, and if I see in the the various stages of processing during the meshing phase, there was some processor communication. That's when we were distributing the mesh. In the setup, we did some communication. When our initialization, we compute things. We do need to keep everything in sync and do some global reductions. In reforming the Jacobian, we have to take into account the overlaps and degrees of freedom between the different processes. So there's communication there. Communication, reforming the residual. Most of the messaging is occurring in our solve, and that's would be what would be expected. And then the post step, that's where we're writing output. And here we're using BTK output. So we had 2 processes, process S0 and process 1. And so process 1 was sending its information to process 0, and that's why with the BTK output, you didn't see it slow down, but it still took, in this case, nearly 10% of the time. And if you want to really start to zoom in on where bottlenecks are, you can zoom in further down a log summary, and you can sort of look at our performance. So that was just it's as simple as that. So let's run our Green's function example. Step 21.cfg-nodes equals 2. Oh, and I keep forgetting I did this yesterday. And when I run in this problem, I need to tell it a problem type because we switched problems. So we need to tell it we're doing the Green's functions problems. So it's computing all those impulses in parallel. And the Green's functions, you can think about, there's multiple ways to parallelize this. You can not only distribute the floating point calculations in sort of a single simulation across multiple cores, but you can think about, because each Green's function calculation is essentially independent, you can use the impulse amplitude spatial databases, and if you want to compute, say, the Green's functions for 2 different faults in a version, you could do one set of simulations on one fault and simultaneously run another set of simulations between the impulses for the other fault, either on a cluster or on your desktop. And so there are, that's another way of using additional processing power, is running multiple simulations at a time. And so I want to point out in this step 21 example, we actually down here at the very bottom of the file, we requested the mesh partitioning information to be written out. And so we basically, this line here, write partition equals true, turns on writing that partition information. By default, it is turned off. We give it, we tell it the data writer, so we're going to do HDF5 output for the mesh. Give it the file name, step 21-partition. And so we can load up ParaView here. This is our old example for this morning. Delete that stuff. Open up examples, 3D X8, output, step 21, partition info. And so here is our 3D mesh. Looks like it was just chopped directly in half. It can pull up this thresholding. And so here I'll put it. So we have process 0 in blue, process 1 in red. We can pull up this thresholding and look at just what process 0 looks like. And so indeed it chopped it right in half. Process 0. Let's go back and make it a little more interesting. Let's run step 3 with 3 processes. So now if I open up my partition file, you notice now I have, I'll turn off the previous one. Here's my 3 partition. And if I threshold this one, so let's look at just process 0. So there's process 0. Remember we have sort of our hex mesh. So it basically tried to take us a chunk out of there. It was not. So when it divides by 3, you'll notice it didn't do just 3 vertical slices across, because the partitioners are going to try and minimize the amount of communication between the different processes. So it basically is trying to minimize, for volume, it's going to try and minimize the surface area of the overlap. And then as you go in 2D, it's going to try and minimize sort of the linear overlap between processes. So in the case of 3, because a cube doesn't sort of nicely chop up into sort of vertical and horizontal cross sections into 3, it did these 2 that sort of take across sort of about 2/3 of the domain, almost a vertical slice when you put them together. And then if you look at what a 3rd process is, it's almost a vertical slice, but not quite. So that's how, in this very small problem, it's pretty hard to come up with an optimal partition when you have these very large elements in a square cube. If we go to, say, 4 processors, I only have 4 cores on my laptop, so that's as high as I'm going to go in this problem. So let's load up our 4. So here you'll see that here's our fault right down here. So it split once across the fault, and then it did sort of a diagonal, not quite perpendicular. And so there's probably almost no difference between this approach and doing sort of the absolute optimal approach that would come straight across here. We also have Duracell boundary conditions on the ends, and so that can also be affecting, our distribution of degrees of freedom. And so that can affect our memory balance as well. So that's how we run in processing in parallel on a desktop machine, how we can look and see how things are divided. When we load up sort of the results of those Green's functions, everything is written. And so here's step 21. If you look at, it's all in a single file, and you see that there's no difference in how I interact with the results of the simulation, whether I've run in parallel or run in serial. So it's relatively transparent after I've run how many processors I've used. Any questions on visualizing the partition or running in parallel on a desktop? I don't see any questions, so we're going to continue on. We're going to go back to our slides.